Today we're going to talk about combinatorial parameters and multivariate generating functions. This is a way using basically the same formal methods to get much more information about the combinatorial structures that we're studying. We're still working with the symbolic method where we have automatic methods for getting from a specification to a generating function equation. And then later we're going to talk about use of complex asymptotics to get an asymptotic estimate for the results, the counting results that we want. But now we're going to focus on getting to the generating function equations. So let's just talk about the basic principles of combinatorial parameters. Up until now, we've really just been counting things, but sometimes we want to know properties of the structures. Like we know that permutations consist of sets of cycles. We might want to know how many cycles we're likely to see in a random permutation on average, or how many leaves are there in a random tree, or how many parts in a random composition or in a partition, or how many subsets are there in a set partition, or average number of times that each letter appears in a random M word. These are all natural questions that we want to know good answers to in practice. And in part one of the course, we talked about all kinds of applications where we studied questions like this in some detail. Average root degree of a random tree is another one. Now, there's one problem with this point of view is that sometimes it's easy to get average case results like this, but they're a little bit unsatisfying. And a famous example of that is an algorithm called separate chaining hashing. We'll look at in a little more detail later on. But basically, it randomly assigns n keys to m lists. And you want to know the average length of a list, it's n over m. But that's a trivial result, but it's not that useful because it doesn't say anything about the length of a particular list. For example, all the keys could be on one list, which would be something that we wouldn't want for performance. So we want to know a little bit more than the average. And really, the techniques that we're going to talk about today, in many cases, can extend to find the full distribution of the combinatorial parameter. For example, the probability that the value is k for all values of k. And with the distribution, you can compute the average, but you can also compute other moments of the distribution that help tell us how likely it is that the thing has a certain value. And we can also compute extremal values like, the first, you could bound the probability that the length deviates significantly from the average, and that's classic in probability. Or we could study like the average length of the longest list or something like that. There's plenty of practical compromises to get some kind of estimate that we can apply usefully in practice. So for this lecture, what we're going to do is look at the basic symbolic methods to help us get generating function equations for parameters. And these, in concert with the analytic techniques that we'll learn later, often can get information about the full distribution of many of these parameters or about extremal values. But really, mostly we're going to be interested in average and standard deviation, and I'll talk about that in just a minute. So instead of talking about the average number of cycles, we're going to say how many permutations of n have k cycles, how many trees with n nodes have k leaves, how many compositions have k parts. So now we have two variables, the number of objects and the value of the parameter. And these are natural questions just rephrased using n and k. And so those are that's the way we're going to be looking at problems studying combinatorial parameters in this lecture. So given that, then let's revisit our definition of what is a combinatorial class. So a combinatorial class is a set of combinatorial objects and an associated size function. That's what we said before. But now we're going to say it may have an associated parameter. That's part of the definition of the class. Every object's got a size and it's got a parameter value. And then given that, then we can write a bivariate generating function, a generating function with two variables. First we'll talk about ordinary bivariate generating functions, just as we did before. And that's simply for every object in the class, we take the first variable z and raise it to the power of the size of the object. And we take the second variable u and raise it to the power of the cost of the object. That's a formal power series of two variables. And we're going to use the same kinds of arguments and manipulation on these two variable power series that we used on the single variable power series before. But they carry the information that we can use to extract moments and other information about the values of parameters, as you'll see. Again, we've got a fundamental identity that again is elementary. If you sum over all objects in the class, z to the size, u to the cost, what you can do is collect, there's a term for every object, and you can collect the terms that have the same size and the same cost, and write that coefficient a n k, the number of objects of size n, cost k, sum on k, sum on n, that's an elementary identity. All of those things, there has to be a term for all of those things in the ordinary bivariate generating function, and that's merely collecting terms, really just as before. We say that the variable z marks the size and the variable u marks the parameter. And actually you could add more variables. And there's a discussion of multivariate generating functions in the text. And again, from the elementary identity, you have the basic answer to the question, how many objects of size n with value k are there? That's the coefficient of z to the n, u to the k in the ordinary bivariate generating function. And again, as I just mentioned, you could add arbitrary number of markers and have multivariate generating functions. I'm not going to discuss that in lecture, but it's covered in the book. So that's the basic definitions. And again, with the symbolic method, we can have transfer theorems, symbolic transfer theorems that give us equations that the generating function must satisfy directly from the specification. And actually, it's the same transfers pretty much that we discussed before. So let's start with a very simple and familiar example, binary strings. So when we introduced the symbolic method, we talked about enumerating binary strings. Now we're interested in some characteristic of binary strings. So they're 2 to the n of binary strings with n bits. But now say we want to know how many n-bit binary strings have k0 bits. So that's a parameter on binary strings. And so for example, the 2-bit binary strings, the number that have 0 bits, there's just one, the 1, 1. The number that have 1 0 bits, there's two of them, 0, 1, and 1, 0. And the number that have 2 0 bits, there's just one. Similarly, for 3, there's just one that has no 0 bits, the 1, 1, 1, and another one that has 3 0 bits, 0, 0, 0, and so forth. And you recognize these coefficients. These are the binomial coefficients. And we know simple combinatorial argument, really from the definition of binomial coefficients, the number of binary strings with k0 bits is n choose k. And we're just using this as an example to illustrate the formal mechanisms that will use the very same mechanisms for more difficult problems. Now, since we have two variables, our ordinary bivariate generating function has two variables, and that's the result. And I'll show two different ways to get that result. That's what the OBGF is. And actually, we often consider these things as two-dimensional arrays. So this is n going down and k going across. And so for 2-bit binary strings, there's 1, 2, 1. That's the distribution for the number of strings that have k 0 bits, and so forth. So those are the familiar Pascal's triangle binomial coefficients. In terms of the generating function, one way to think about it is to write is to evaluate one of the sums. So if we evaluate the sum n choose k u to the k, we get 1 plus u to the n. So then 1 plus u to the n is the coefficient of z to the n in a generating function. And that's called the horizontal ordinary generating function for this problem, coefficient of z to the n. And what it does is it gives the distribution of the number of k bits in n-bit strings. 1 plus u to the n. It's a generating function for the number of k bits in n-bit strings. There's one with 0. There's one, this is for 7. There's one that has 0 1 bits. That's all ones. There's one with 7 1 bits. That's all zeros, and so forth. That's the distribution. We call that the horizontal generating function. And sometimes, in fact, many times, what we'll do after finding the ordinary bivariate generating function is extract coefficients in this way to do the analysis, and we'll see examples of that. Or we can go the other way and evaluate the sum on z. So switch order of summation, evaluate the sum on z, sum on the upper index, n choose k, sum on n, z to the n, is z to the k over 1 minus z to the k plus 1. So that's an elementary generating function identity. So if you look at that function, which we call the vertical OGF, as a generating function where u is the variable, the coefficient of u to the k is z to the k over 1 to the k plus 1. And so that's another way to analyze this generating function. So it gives for a fixed k, it'll give the number of strings with k bits as n increases. So there's 126 9-bit strings with 5 bits and so forth. So now evaluating either one of those sums, maybe the horizontal one's the easiest or most familiar one. If you sum 1 plus u to the n, z to the n, well, that's just summing the quantity z times 1 plus u to the nth power over all n. So it's just 1 minus that 1 over 1 minus that quantity. That's how we evaluate the ordinary bivariate generating function for binomial coefficients. So for many of the problems we study, we'll be looking at these various different ways to look at the ordinary bivariate generating function. But people are familiar with the binomial coefficients, so this is a good table to refer to check your understanding of this terminology. So now let's look at the symbolic method for ordinary bivariate generating functions. It's the same setup as we've used before in lecture 1 for just regular single-variate generating functions. If we've got classes and we have their ordinary bivariate generating function, z marks size, u marks a parameter value, then if we do an operation like disjoint union, the same operation that we talked about before, then the ordinary bivariate generating function just translates to the sum. We'll look at the proof. It's an elementary proof just as before. Cartesian product translates to the product of the generating functions, again, just as before. Sequence translates to 1 over 1 minus, and again, that follows from product just as before. So the same constructions, these are the same constructions, immediately give us expressions on the ordinary generating function. Now what we do with those expressions is a bit more complicated, but the generating function equation part of the problem is very much as before. So immediately we get the ordinary bivariate generating function equation. Now this also, if we wanted to include other variables, we could also expand this transfer theorem to hold for generating functions that have multiple marked parameters. Okay, so, and these are the proofs of the correspondences, and there's no need to go into these in much detail because they're very similar to the ones that we did for single variate generating functions. And it's simply a matter of rearranging terms according to the definition. If we've got an object C in A plus B, then either it's in A or it's in B, so we can split out the terms for those in A and for those in B, and that's the proof of the transfer theorem. For Cartesian product, we have, since there's pairs of objects, we have a double sum, and then we can, those sums are independent, so we can rearrange terms to simply get the product again, just as before. And for sequence, a sequence of length k is a to the k, so the generating function is azu to the k, just applying the product rule k times. Or a sequence of any length, it's where actually for any subset of the integers, you can just expand the previous two rules to get an expansion like that. And for sequence of all integers, just 1 over 1 minus, just as before. So all those correspondences are immediate, but we don't need to look at the sums anymore because we'll just use the transfer theorems, which are natural extensions of what we've done before. So here's an example of using the symbolic method to derive that ordinary bivariate generating function for 0 bits in bit strings. And it's the same setup that we've used many times, except now we add the parameter. So our class is the class of all binary strings. Our size is the number of bits in the string. Our parameter is the number of 0 bits in the string. So our ordinary bivariate generating function on the two variables is the sum for every object b, z to the size of b, u to the number of zeros in b. Our elementary identity says that we can collect terms that have size n and cost k, and that's we'll have b and k of those. This is all elementary from the definitions. So our construction now is the same as before, except that what we're going to do is put a variable u for every 0 bit. So before we had sequence of 0 bits and 1 bits. Now we have sequence of marked 0 bits and 1 bits. We mark the 0 bits but not the 1 bits. And that's it. Now the transfer theorem immediately translates that to this ordinary bivariate generating function equation. uz0 translates to uz and z1 translates to z. So we have a sequence operation applied to a class whose generating function is z times 1 plus u, and then the sequence transfer says it's 1 over 1 minus that. So that's immediate derivation of the ordinary bivariate generating function for this class. Again, we can, in this case, with binomial coefficients, we can go ahead and expand and calculate the coefficients b and k, which is exactly n choose k. So in this calculation, what we do is we look for the coefficient of z sub n in bzu, thinking of u as a constant. So it's 1 over 1 minus z times 1 plus u. That expands to sum of 1 plus u to the n z to the n, so the coefficient of z to the n is 1 plus u to the n. And then we want coefficient of u to the k in that, and that's n choose k. Or you could do it the other way around and find the vertical generating function first. The point for this lecture is the equation that defines the generating function is immediate. And that's the basic idea behind using the symbolic method to study combinatorial parameters. So those are the basics. Now we'll look at some real examples.